Greetings, Pak Aditya. We are from Group 5 with the topic of starting and ignition for the jet and rocket propulsion UTS. So first of all, the table of contents, we will be talking about the basic concept of starting, basic concept of ignition, recent advances in starting and ignition, and also the conclusion. So first of all, the basic concept of starting. So basically, the starter motor must produce a high torque and transmit it to the engine rotating assembly in a manner that provides smooth acceleration from rest up to a speed at which the gas flow through the engine provides sufficient power for the engine turbine to take over. You can look that the first one is, sorry, at the graph on the left, that is the graph that shows the value of RPM and TGT or turbine gas temperature with the timing. So next on to the method of starting, first of all is the electric starter, which is usually a direct current electric motor coupled to the engine through a reduction gear and ratchet mechanism or clutch, which automatically disengages after the engine has reached a self-sustaining speed. The full voltage to be progressively built up as the starter gains speed. It also provides the power for the operation of the ignition system. The electrical supply is automatically cancelled when the starter load is reduced after the engine has satisfactorily started or when the time cycle is completed. The starter motor is next. The cartridge one is basically a small impulse type turbine that is driven by high velocity gases from a burning cartridge. The power output of the turbine is passed through a reduction gear and an automatic disconnect mechanism to rotate the engine. An electrically fired detonator initiates the burning of the cartridge charge. The next one is as isopropyl nitrate. This type of starter provides high power output and gives rapid starting characteristics. It has a turbine that transmits power through a reduction gear to the engine. In this instance, the turbine is rotated by high-pressure gases resulting from the combustion of isopropyl nitrate. This fuel is sprayed into a combustion chamber, which forms a part of the starter, where it is electrically ignited by a high-energy ignition system. A pump supplies the fuel to the combustion chamber from a storage tank, and an air pump scavenges the starter combustion chamber of fumes before each start. Next, method of air starting. An air starter motor transmits power through a reduction gear and clutch to the starter output shaft, which is connected to the engine. The starter turbine is rotated by air taken from an external ground supply, an auxiliary power unit, or as a crossfeed from a running engine. The air supply to the starter is controlled by an electrically operated control and pressure reducing valve that is open when an engine start is selected and is automatically closed at a predetermined starter speed. The clutch also automatically disengages as the engine accelerates up to the idling RPM and the rotation of the starter ceases. Next, the method of gas turbine. It's used for some jet engines and is completely self-contained. It has its own fuel and ignition system, starting system usually electric or hydraulic, and self-contained oil system. This type of starter is economical to operate and provides a high power output for comparatively low weight. The starter consists of small, compact gas turbine engine, usually featuring a turbine-driven centrifugal compressor, a reverse flow combustion system, and a mechanically independent free power turbine. The free power turbine is connected to the main engine via a two-stage epicyclic reduction gear, automatic clutch, and output shaft.
Of the ignitions, there's a type which is DC Trembler operate unit. It is an induction coil operated by the Trembler mechanisms, charge the reservoir capacitors through the high voltage rectifiers. So when the voltage in the capacitor to the breakdown value of the cell discharge gap, so the energy is discharged across the face of the igniter plug. And the choke is fit to extend the duration of the discharge, and the discharge register is fitted to ensure that any residual stored energy in the capacitor is dissipated within 1 minute of the system is switched off. So the safety register is fitted to enable the unit to operate safely even when the high tension grid is disconnected and isolated. There's another type which is transistorized ignition unit. So the operation of the transistorized ignition unit is similar to that of the DC trembler operated unit, except the trembler unit is replaced by a transistor copper circuit. So, such as the unit has many advantages over the trembler operated unit because it has no moving parts and gives much longer operating life. Therefore, the size of the transistorized unit is reduced and its weight is less than that of the trembler operated unit. Next. There's another type which is AC ignition unit. It receives an alternating current which is passed through the transformer and rectifier to charge a capacitor. So when the voltage in the capacitor is equal to the breakdown value of the sealed discharge gap, the capacitor discharges the energy across the face of the igniter plug. So the safety and discharge resistor are fitted as in the trembler operated unit. Next, there's the surface discharge igniter plug. It has the end of the insulator formed by a semiconducting pellet which permits an electrical leakage from the central high tension electrode to the body. So when the voltage in the capacitor is equal to the breakdown value of the sealed discharge gap, capacitor discharges the energy across the face of the igniter plug. So this ionizes the surface of the pellet to provide a low resistance path for the energy stored in the capacitors. So the discharge takes the form of the high intensity flashover from the electrode to the body and requires potential difference of approximately 2000 ports of operation. Next, there is the rewritings. The jet engine requires facility for rewriting should the flame in the combustion systems be extinguished to bright. But the ability of the engine to relight will vary according to the altitude and forward speed of the aircraft. So a typical relight envelope showing the flight conditions under which an engine will obtain a satisfactory relight.
So to continue, this is the recent advances on starting. So a design is proposed. A design of the proposed control unit is shown in Figure 2. The modern control unit consists of several basic blocks, namely MCU, microcontroller control unit, power supply for MCU, safety lock, control panel, and 3 switching circuits for the electric starter, fuel pump, and the ignition system. The control panel, where all press buttons, switches, and LED indicators are situated, is a standalone part, wired to the control unit via cables. After the realization of the control unit prototype, a set of function evaluation measurements was conducted. The manufactured prototype has been connected to the jet engine and several test startups have been performed. Test results show that the newly designed control unit works properly, which confirms the measurement records shown in the figure on the right.
So on this paper, we will look into the UAV system with the jet engine and the control strategy of the starter generator. In the developed UAV system, only the starter generator is used for starting and cooling, which eliminates the use of APU. Furthermore, the starter generator connects directly to the jet engine and rotates at high speed for miniaturization. The challenge of this paper is the achievement of stable operation through the proposed control strategy, even when the starter generator transits amongst operation models, i.e., starting mode, powering mode, and cooling mode without the APU and reduction gears. The figure on the right, as you can see, shows the experimental results of the jet generator operation with the exhaust nozzle temperature control, as shown in the figure. Even when the rotation speed accelerates or decelerates, the exhaust nozzle temperature converges to the command value. The exhaust nozzle temperature can be controlled within the maximum deviation of 2% compared to the command value in the steady state. Furthermore, the exhaust nozzle temperature at 70,000 R per minute drops to 700 Celsius because the inflow current of the battery is limited. Also in this paper identifies and examines the symptoms during starting a dynamic measurement system with a photoelectric system and quick thermocouple is used. The flame signal detecting system was used, which is converting the flame's radiated energy into electricity and transmitted to a combined amplifier and recorder in order to monitor the ignition time delay and the unstable and stable combustion for 4 parameters. 1 equals to rotor speed, 2 gas temperature, 3 fuel flow rate, and 4 flame signal. They're all which is all evaluated in order to optimize engine start. It is clear that the fuel burns in 3 distinct phases: A, ignition delay; B, the fuel lights up with unstable combustion; and C, stable combustion. So therefore, the conclusion of this paper can be that the ignition delay and stable combustion signal can be precisely and dependably detected using the photoelectric detector installed on the combustor casing.
So I'll continue. In this paper, there is a 3-sector combustor with improved optical access that has been built to comprehensively examine the phase flow ignition process. The combustor design makes it possible to study the full combustion process, including how the energy builds up and how flame spreads over the various sectors. The facility provides pressure as low as 0.4 bar and air-fuel temperature as low as 233 Kelvin. And the silica windows are used to sustain high temperature. Both main burner ignition sequence and starting injector ignition performance have been tested against those of full annular combustors. Future research should incorporate interferential filtering and enhance high-speed cameras to enhance flame visualization, particularly for flame propagation between burners. In order to describe the flow structure inside the combustor, optical diagnostics like PIV or LDA should be investigated. The next one is, there is a theoretical analysis that is accomplished by developing a mathematical representation of the combustion model and combustion conditions. The feasibility of using diesel as a small turbojet fuel is investigated using numerical simulation tools. The 3 primary areas of research are the improvement of the combustion chamber and evaporator, the selection of injector position, and the endurance of fire. A consistent temperature of 1200 degrees should be used for the igniter. The igniters needs to be properly preheated before starting the fuel pump. The result of this paper and experiment can be the rotor speed increase with the increase of fuel supply after successful ignition. As the fuel supply increases, the ignition time increases. The data in the table show that this starting technique is highly reliable and that the turbojet operates steadily after it has started. After observing this condition of the combustion chamber, diffuser, and bearing seat as shown in the figure. So that's all for our presentation. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.